Okay guys, so this is the last video here in the spectroscopy series. Hopefully you've made it this far. If so, congratulations to you. This time we're going to be talking about the decay of excited states. And there are two basic processes through which the excitation energy of an excited molecule can be discarded. One is radiative, where the excited state emits a photon. And there's two processes in that subcategory. Fluorescence. In fluorescence, the decay of the excited state ceases as soon as you turn off the excitation source. So suppose you had a UV lamp that you were using to excite some electronic transition in your system. The fluorescence will continue as long as the UV light is turned on, but as soon as you turn it off, the molecules will stop emitting photons. Contrast that with phosphorescence, where the emission process will continue long after, in some cases, the excitation source has been turned off. And that is highlighted here in this figure. It's showing us that the fluorescence decays very quickly after the excitation source has been turned off, whereas phosphorescence kind of lingers on for a long period of time and is a very slow process. The other category of decay involves non-radiative processes, and so this is where the excitation energy is transferred essentially as heat through collisions with its environment. Other things that can happen, you can dissociate your molecule, so you can excite the molecule and then it can fall apart, and so the excess energy is lost in the fragments that are produced. You can also have chemical reactions that take place, and so you can lose energy through those processes. And then at the end of this section, we'll talk about a stimulated emission and lasers. And so this is an application of the decay of excited states, where you force the decay through stimulated emission. So we'll talk about fluorescence first. Fluorescence involves a fast conversion of the excitation energy into re-emitted light. We'll consider a simple two-level system. So S0 is our ground electronic state. S1 is the first excited electronic state. And each of these have their own manifold of vibrational states, like we talked about in the last video. When you have absorption, you go from the ground vibrational state of S0 to the excited vibrational states of S1. Once you get up to one of these excited vibrational states, the molecules very quickly relax through collisions down to the ground vibrational state of the upper electronic state. Okay, so we have a very fast vibrational relaxation on the upper electronic state. And then once you're at the ground vibrational state of S1, it takes a little bit of time, but eventually S1 will lose energy through the emission of a photon, which will take the system to one of several excited vibrational states on the ground electronic state. And so these ideas are depicted in this picture here. We have the potential energy curve for the ground electronic state. So as a function of, let's say we're considering a diatom, as a function of the internuclear distance, this is how the ground state's electronic energy looks as a function of R. And then there's going to be several vibrational energy levels for the ground electronic state. Up here we have the excited state's potential energy curve, and these are the vibrational levels for the excited state. And when you undergo absorption from the ground vibrational state of S0, you probe the various excited vibrational energy levels of S1. Now, once you promote the molecule to one of these excited vibrational states through the process of collisions, the molecules will very quickly lose that excess vibrational energy and will relax down to this ground vibrational state of S1. And from here is where you will get emission of a photon via fluorescence. And this will involve transitions to the various vibrational states of the S0 electronic state. So absorption probes these vibrational levels on S1, emission probes the vibrational energy levels on S0. One consequence of the energy differences here is that the absorption wavelengths will be much shorter, not much shorter, but they will be shorter than the wavelengths of the emission, right? This is a large energy difference, and so it will involve short wavelengths. This is a smaller energy difference, and it will involve longer wavelengths. So absorption occurs at higher frequencies and shorter wavelengths than fluorescence. Moreover, that vibrational fine structure that I've alluded to when discussing the transitions to these levels and the transitions down to these levels, the intensity patterns that you get for absorption and fluorescence can be the same or they can be different. It just depends on the particular electronic states that you're looking at. This is essentially what I've already said, is that the absorption fine structure is due to the S1 vibrational states, whereas the fluorescence fine structure is due to the S0 vibrational states. Notice this transition here, the 0-0 transition. I'll go to the diagram. And so that would be a transition from here to there, and then you also have in the fluorescence a transition from there to there. And so in this diagram, those would be exactly the same frequency and wavelength. However, the two transitions could be different from one another due to the interaction of the chromophore with its solvent environment. So sometimes the 0-0 transitions are the same, other times they are different. In this particular example, the 0-0 transitions occur at the same wavelength. What we see here at lower wavelength and higher energy is the absorption curve. And the vibrational structure that you're seeing here is due to the excited electronic states vibrational energy levels. At longer wavelengths, we see the fluorescence, and the vibrational fine structure that you see here are due to the vibrational energy levels on the ground electronic state. In this example, the pattern that you see is basically symmetric between absorption and fluorescence. And that's indicative of the excited state geometry being very similar to the ground state equilibrium geometry. That is, the shape and position of the excited state potential energy curve relative to the ground state curve would be more or less the same. In this diagram, they're very different. And for that case, what can happen is the fluorescence pattern will be radically different than the absorption pattern. So sometimes the absorption and fluorescence are mirror images, other times they're not. This cartoon is meant to illustrate why the 0-0 transition for absorption might not occur at the same wavelength as that of fluorescence. And so you have some chromophore in its ground state. The solvent is caging that chromophore in solution, and there's a particular interaction between the chromophore and its surrounding solvent molecules. And those interactions will be different for the excited state chromophore. So in absorption, you're probing a chromophore that has the ground electronic states solvent configuration. But in fluorescence, when you fluoresce from this state, here the solvent has accommodated the excited electronic state. So the solvent environment can be different for the excited state than it is for the ground state. And when that's the case, you're going to get a difference between the 0-0 transitions. So next we'll talk about Phosphorescence. Phosphorescence involves an electron spin flip, and so we need a three-level system to describe phosphorescence. So we'll consider a singlet ground state, a singlet excited state, and a corresponding triplet excited state. Okay? And so here's what happens in fluorescence. You have absorption like normal. You go from the singlet ground state to the singlet excited state and different vibrational states of that excited state singlet. In the course of vibrational relaxation on S1, the system, in the case of phosphorescence, undergoes an intersystem crossing that takes it in a non-radiative way from the excited state singlet to the excited state triplet. That triplet can then relax down to its ground vibrational state, and then you'll have emission from T1 to S0 and various excited vibrational states of S0. However, this process is spin forbidden because you're going from a triplet to a singlet state, and there are selection rules against that type of thing. However, when the spin orbit coupling within the electronic system is large enough, you can bend these selection rules. So even though the process is so-called spin forbidden, it can still occur. It just occurs with a very small rate. Hence, phosphorescence is a slow process. So here's the diagram depicting the phosphorescence process. You've got the ground state singlet. You've got the red curve here is the excited state singlet. And then you've got this excited state triplet. And the triplet has a lower energy than the singlet, always. And so what happens is you absorb up to the singlet, vibrational relaxation occurs, but at a certain point, the potential energy curve for the triplet and the singlet cross one another. And it's at this region of both space and energy that you get this intersystem crossing occurring, and so you'll have a non-radiative transfer from the singlet to the triplet potential energy curve. Then the triplet will relax down to its ground vibrational state, and then you can have the emission, the phosphorescence, occurring from there, and you can probe the different ground state vibrational energy levels. The reason that the phosphorescence is observed at a lower frequency and longer wavelength than fluorescence is because the triplet has a lower energy than the corresponding singlet, always. So you'll always see phosphorescence at a longer wavelength than you will the fluorescence. A diagram called a Jablonski diagram is used to illustrate these types of processes. Here's an example of one. It shows us the vibrational energy levels on the ground state singlet state, the vibrational energy levels on the excited singlet state, and similarly for the triplet state. The fluorescence, so fluorescence from S1 down to S0 is a direct path. It has a shorter wavelength than the phosphorescence, and then the intersystem crossing is indicated here. You go from the singlet excited state to the triplet state, and then you phosphoresce down from there. Now there's another process called internal conversion that we'll talk about in just a little bit. Just a couple more comments on fluorescence versus phosphorescence. Which is going to be dominant? That's the question here. Well, for processes where that excited state singlet undergoes vibrational relaxation very quickly, that tends to favor fluorescence because there's not enough time for the intersystem crossing to occur. So if the excited state undergoes very fast vibrational relaxation, fluorescence is going to dominate. However, in systems where like solid phase systems where there are far fewer collisions happening, which means it's going to take a long time for the excited chromophores to vibrationally decay, there's going to be a larger chance for phosphorescence to occur. So in solid phase emission, that tends to favor phosphorescence a little bit more. Another type of situation where phosphorescence would be favored is when you have large, heavy atoms in your system. This tends to increase the spin-orbit coupling, which is necessary to have intersystem crossing. And so that'll make the intersystem crossing more likely, and phosphorescence will be more favorable in those situations. And that's represented here in this problem. The observation is that fluorescence efficiency decreases, and fluorescence efficiency decreases and phosphorescence efficiency increases in this series here. Here, I'm going to pause this just for a second here.